So hello, welcome to everybody. What we see now is the fourth week lecture of the topic which is called Drive Techniques here at the Technical University of Budapest. And this lesson will talk about the so-called two-stroke engines. This is a live stream, so there are some students present in the classroom, other students are watching online. So either I will speak to the students in the classroom or I will speak to the students that are outside the classroom. So maybe everything will be okay, the network bandwidth and so on will be okay. If you don't hear me or there is any problem with the stream, please write your message on the chat window next to the YouTube main window. And also if you got any questions, note that there is usually 30 to 60 minutes delay in what you see and what I'm talking. So the transmission requires some time. And for that reason, while you type your questions, it takes a bit time so that I could see it and I could answer it. So I'm kindly asking for your patience. Now, and then let's start the practical things. Last week we were talking about engines globally. We were discussing the different working cycles in thermodynamics like Otto cycle and diesel cycle, and also we were talking about Monsieur Lenoir and his three-stroke engine. And now let's jump one step forward. We consider one given way of power increase of the engines. And for that, let's try to start with our basic equation. If I'm not wrong, I may say the power of an engine can be computed as force times speed. And for a force, I may say I get an indicated pressure that comes from measurements. This is a mean pressure coming from the thermodynamical process times the cross section of the piston. That gives a force. And what about velocity? Velocity can be a mean velocity of the piston, and the mean velocity of the piston can be given as 2 times s times n, where s is the stroke of the engine. So do not confuse with the medical stroke and any other applications of the same word. So pi times a piston times 2. Why is this 2 there? That's because if we are talking about a classical four-stroke engine, then we need one up and down. That means one. Wait a bit. I'm thinking about one up, one down. This is 2 strokes, yes. Times 2 r, r being the radius of the crank, and n being the number of rotations, actually. And if we get, what else we get? If we get also the number of strokes, then we have to add one more member here. And this one more member, supplementary member, I put it somewhere here. This is 2 divided by I. And also I put here, this is 2 divided by I, where I was the number of strokes, isn't it? 2 for 2-stroke and 4 for 4-stroke. I hope I was not really wrong here. If yes, you will take it. You will tell it in the remarks or in the chat window. Now, and we are starting from here. How we can increase the power of an engine? Either we use a higher pressure inside the cylinder that increases the indicated pressure level globally, or we use a larger piston diameter or piston surface, or we use a larger radius in the crank mechanism, or we use larger number of revolutions by minute, or we try to get one work stroke by rotation instead of just one work stroke by 2 rotations of the crankshaft. Okay? So I will talk about this I, where I say I equals 2, this is a so-called 2-stroke engine. And I equals 4 for the so-called 4-stroke engine. And I make here, what's the say in English? What is the name of the English of this? Sorry? Quotation, thank you. Quotations, because actually every engine works upon 4 strokes. The so-called 2-stroke is a kind of redistribution of the workplace or of the work quantity somehow, so that I could have a work stroke in every rotation of the crankshaft. No. So how it is possible, basically, roughly? One possible over increase, I say a work stroke in every rotation. If I want a work stroke in every rotation, that has a consequence, and the consequence is that I cannot use the top of the piston and the cylinder volume in the top of the piston for all the classical parts of the 4-stroke process. So in the 4-stroke process we get admission, compression, work stroke plus exhaust, but it needs 2 complete crankshaft turns. What to do if I want to have just one crankshaft turn for that? I've got to put something elsewhere. And this something can be the admission, this can be the compression, or any other possibilities that I will enumerate shortly. So, we need separate solution for either intake or admission. More officially, I apologize for my English, it's not the best as usual. For admission, and also it can be something separate for compression. Usually work stroke and exhaust happens, and also it can be something for the exhaust. Exhaust, let's say I put it in brackets, but still it happens. Okay, so either I can have different machines for that and different places, because these things will not fit either in time or in the place, in the volume of the cylinder. And for that, I may have different solutions. The advantage, shortly, of these solutions is that I get a work stroke at at each crank turn. And disadvantage for sure, I will have additional machines, parts required, and usually losses below, let's say losses below N max divided by 2 RPM. Okay? And also losses in flow dynamics, or flow mechanics. So these are the global solutions, or the global observations. And what is to be clarified here, that remark, it's a remark that these engines still work upon the 4-stroke principle. And the 2-stroke expression is just a, let's say, commercial name for that. Okay? And for the sake of simplicity, I will call these solutions in the further things as 2-stroke conditions, okay? Good. So, usual name, two-stroke engine. So in quotations, it's a two-stroke engine, and I will call it like that in the things that come. Okay, so if it's clear, do you have any questions? No? No? Online? If any questions, you put it in the chat window and I try to answer it. So now let's see the practical solutions for such engineering task. Shortly, two-stroke engine. Principles. Let's start with the gasoline engine. Which is more common. The first solution is what we call the crankcase pump. So I told you that the admission and the compression should be removed or put in another place for improving the efficiency of the engine, or let's say improving the equation value describing the engine. And for that we use a pump for sure. And this crankcase pump looks the following. You get a piston that is in the cylinder. You get a crankshaft. Let's say you get a connecting rod connecting the crankshaft and the piston. And what else you get? For sure, you get a specially formulated crankcase, where you get admission directly into the crankcase, so not on the top of the cylinder but below. Then you get different conducts that orient the flow. Wait. It's better if it's there. That orient the flow from below the piston to upwards. And here somewhere you get the piston at the upper surface, and you get a kind of canalization system, a canal system or port system. So admission goes here, exhaust goes here. And what happens if the piston moves? Logically, if the piston moves upwards on the lower volume, you get admission as the volume increases. So the external pressure goes in. Meanwhile, up above you get compression. Then, if there is work stroke on the top of the piston, then you get a partial compression below in the crankcase zone, plus you get a flow that goes upwards from the crankcase to the top of the piston. The flow regulation is going through ports. These are called ports in the English literature: admission port, exhaust port, and scavenging port. So admission port, you get exhaust port, plus something new, special to the two-stroke engines, the notion of scavenging. Scavenging port. And scavenging, or it is also called transfer port, that links the two volumes below the piston and above the piston. Okay, and how these ports are opened or closed? They are closed or opened by the piston, controlled by piston motion. The piston just covers either the admission port or the exhaust plus the scavenging port. Okay, the piston side, I say. And for that reason, we don't need valves at all. We don't need complete camshaft and camshaft drive system at all. Instead, we need special bearings for the crankshaft, special bearings for the connecting rod, because we don't have a closed lubrication system. We are obligated. We have to guide the fuel and the fuel-air mixture through the crankcase. So usually what we do, we mix the oil, lubricating oil, directly into the fuel. And so here there's a quite poor lubrication, and we use roller bearings that support quite well the lubrication by oil mist, oil fog. So it's just small particles in the air and not a direct oil flow driven to the lubrication points. Okay? This is the basic idea of the crankcase pump. There's also a second solution. The second solution looks like the following. it here. Crankcase pump version 2. Crankcase pump version 2. When you get well, what is the English name of that? I will see the word soon. So the layout is the following. You get your main piston. You get your crankshaft. You get your connecting rod. And what else you get? You get a secondary piston. Or a scavenging piston here. So 2 pistons on the same crank pin. And what's the task of this secondary piston? It has just a unique task, and this task is to modify the volume of the crankcase. Nothing else. So if I want to draw this, system, this secondary piston has the unique task to modify the volume. I get a cylinder wall like this, and I should have admission somewhere here, like this. Okay? This secondary piston does nothing else than changing the volume of the crankcase.
Modifying the volume will lead to better efficiency or just efficiency?
Yeah, you are right, because you get a secondary piston. To modify the crankcase volume, crankcase volume. The advantage is helps admission and also helps scavenging. So better flow efficiency. It is an ETA for efficiency, better flow efficiency, which is purely good thing. Why don't use this at all? That's because we get higher friction. So this secondary piston has also rings. So there is friction on the cylinder wall, and this is really, really bad. So helps admission, helps scavenging. There is higher delta V volume variation and higher pressure variation in the crankcase. But if I say higher friction losses, then I say this is really huge. So it was used in the 1930s in racing motorbikes in Germany, and these motorbikes could be recognized by their huge fuel tank regarding to the other four-stroke engines. So if, let's say, the specific consumption, have you heard about the specific consumption, gram by kilowatt hours, numbers a bit, not so much? So here you get a normal two-stroke engine has got a specific consumption about, let's say, 250, 300 gram by kilowatt hour. An engine like that, it goes up to 400, 450 gram by kilowatt hour. So let's say 1.5 times an ordinary two-stroke engine consumption. So it's quite theoretically it's a good solution. In practice, it has some disadvantages that can happen. So we have forgot this solution quite quickly, and we got better solutions. Okay, so I just noted it is DKW and the 1930s. Then it was popular. It's a solution that officially, or that actually works, but it's not the best one. A more efficient solution is what we call a split cylinder engine. How it looks like. It looks quite strange actually. You get one cylinder and one piston, which is of small diameter. You get somewhere here a crankshaft. On the crankshaft, let's say, I try to make a better sketch than I made before. No. You get a crankshaft somewhere here. And you get also a second piston here. They should be more or less similar. I apologize for that. I tried to make a better sketch. No. Two identical but small pistons, small bore, large stroke. And they are linked somehow. One connected rod, second connecting rod. And if I look at the cylinder, I will see the following. First piston admission as usual, a large crankcase, then you get here a transfer port or scavenging port, you get the cylinder wall, and also you get a cylinder wall in the middle, plus you get exhaust here, and you get a cylinder wall till this level, plus you get a common combustion chamber. The top of the cylinder is somewhere here. Do you see? What was the advantage of this system? It was produced for a long time, let's say for 50, 60 years. Here you get the admission. Here you get the exhaust. And what happens then? The admission goes down as in a classical crankcase pump. The scavenging goes upwards as in a classical two-stroke. But when the flow comes out here, it goes in the left cylinder. Meanwhile, the exhaust happens out in the right cylinder. So what happens with the flow? The flow is practically pushing the exhaust, so there is no mixing of fresh air fuel and the burn gases. Usually there's a wall, a surface that separates the two, but there is no uncontrolled swirl inside the combustion chamber.
This means more efficient way to make the exhaust out of the cylinder.
Exactly. So here the flow makes a loop like this, or a half turn like this. And this system is quite efficient, though it's a two-stroke system. And also it still has two pistons, as in the previous case, but as both pistons participate in a work stroke and also in size. Both pistons have got piston rings, but these piston rings have got smaller friction surface than in the secondary piston case. It's much better. So this solution has the advantage to have clean flow directions and minimal loss of fresh air fuel mix. So the air fuel mix cannot be mixed by the exhaust gas and will not go just directly through the cylinder to the exhaust, because there's a wall in the middle. It has to follow a given path. But still, there are some disadvantages, like important friction still, and also to avoid high friction, you get small N max RPM. If I say small, I say in the order of 4,000, and for sure not over 5,000. It's like a diesel engine, let's say. So small RPM range. And also important heating of the cylinder wall. Because the cylinder wall between the pistons has got problems with the cooling. Nevertheless, by the time the pressure, the power was not so important and the efficiencies was more important at low RPMs, this solution was really, really popular. You get very nice cylinder castings. So 2 cylinders, 2 bores, and complicated admission and exhaust canals. So this was really an art in casting to make such cylinders in one unit. And if you look at the internet, you see such cylinders in Puch, or Puch in German. And also the other German company this was from Austria, and from Germany you get Triumph. And Triumph exists also in England. So the German Triumph was called Triumphwerk Nürnberg. So it was TWN. Triumphwerk Nürnberg. These were the 2 manufacturers that used these solutions. Puch used it from the 1920s till the late 1960s, 1970s. And if you see such cylinder, which is a long cylinder, because of the twin pistons, and you see just one carburetor and one exhaust port, you can know that it's a split cylinder engine. It has typical brum 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 noise, a low frequency noise, much lower than the usual 2 strokes, because of the lower RPM and also because of this uniform unidirectional flow. And if you don't rev it, it's quite an efficient engine, because low speed, low friction, and at low RPMs it has a good efficiency. Not as good as a 4-stroke, but still not so bad for a 2-stroke. Okay. If it's clear, and there are no questions on the chat, as I see, then I go to explain about scavenging a bit. About scavenging, yeah, I got to erase the table. So here, erase the board. So a bit about port control. The question was how to orient the gas flow without valves. Because if you have got just a hole on the side of the cylinder, which is opened or closed sometimes by the piston, then it's quite difficult to see what happens if the piston opens or closes the thing, how the gas will enter or go away of the cylinder. You need some ideas about flow dynamics to see what happens. And the first solution was a so-called deflector on the piston. So you had a piston that looked like this. And you had the crankshaft here. You had the connecting rod here. So when the flow entered in the cylinder from the crankcase, then what happened? It went against this deflector on the top of the piston and had to change its orientation and went up in the combustion chamber. So it was a quite common solution in the early two-stroke engines. The disadvantage was that the piston was heavy and also complicated to manufacture. It's heavy. Piston. And complicated. Manufacturing. Complicated manufacturing also. So it was clear quite soon that the best way is to use a flat top piston as for four-stroke engines. But then how to orient the gas flow in the cylinder? If there are no valves, just open, closes, and the gas goes in. And if the exhaust is just in phase, it goes also out, which is quite bad for the efficiency. And the idea was that of Mr. what was his name? Adolf Schnürle, if I'm not wrong. Schnürle was a German guy that worked on flow mechanics, and he was working at this time in China, in Nanking, southern China, at the university, because there were German colonies in this time in China. It's just 100 years ago. Huh? And the guy observed the following. It has the idea. So let's say Adolf Schnürle. Schnürle around 1925, roughly. He said, okay, we can draw the thing in plan, but also we can draw the thing in space. And once we draw the thing in space, we can observe the following. If we get the piston, we draw the cylinder around just the upper part of the cylinder. And if we don't put the scavenging port or transfer port in opposite of the exhaust, so here you get the exhaust, but we put it somewhere on the side under an angle, then interesting things can happen. What are these interesting things? I need a top view of the system for that. In the European representation, the top view is just below. I get the piston pin here, and I want to show you about the idea of Schnürle. We get what we get. We got the exhaust still. We got just one exhaust. But what happens if we get, instead of one, what happens if we get two transfer ports? And these two transfer ports goes where? It was a bad orientation, sorry. These two transfer ports goes like this, oriented in the space. So they come from that side somehow. If the transfer ports have got an orientation in the space under at least two angles, so you get a first angle regarding to the horizontal here, let's say alpha 1, and here regarding the vertical to this, this is the horizontal plane, and in the vertical plane you get, let's say you get here alpha 2. What happens in this case? You orient your gas flow by the canal, by the port. And how the gas works in these conditions? The gas goes, I'll try to use a different color. The gas goes here against the rear wall of the cylinder. Then it has a shock. And it changes the orientation, goes upwards. And then again it has a collision against the combustion chamber, and then goes out of the cylinder. If you want to draw it here, you get this thing, and then you get this thing in the plan. And what the flow makes, it looks like a loop. So this is what is called loop scavenging. Here you can have a flat top piston, and also you can have better flow, so better efficiency, eta efficiency. You get a better efficiency in the system. Okay, is it clear? So globally, if you get this layout, you have arrived to what you see actually in small chainsaws and also in lawnmowers, small lawnmowers for cutting the grass. This is what exists still today, 100 years after. You used first, this was patented by the so-called DKW company. This was a German motorbike and automobile company, which is a part of what is known today as Audi. You get the four circles of Audi. This is one circle of Audi. Okay? So the first Audi was a two-stroke engined car. And then, after the Second World War, all the German patents were free to use because Germans have lost the war. So the world started to use these machines after. Do you see this principle after? Is it clear? Okay. Now. Consequence of that. A two-stroke engine operates upon the principles of fluid dynamics, fluid mechanics. So here for a two-stroke engine, you have to be good in fluid mechanics if you want to improve the power of the machine. And also a second result, or a consequence of this is that optimization of the flow can be optimal only in a narrow RPM domain. So, as you are working in fluid dynamics, you got frequencies and you got critical speeds in your system. And by orienting the angles alpha 1 and alpha 2, you can make good things, but these good things depend on the speed of your gas flow, and the speed of your gas flow is linked to your RPM. So you may get huge power out of your two-stroke engine, but huger is the power, narrower is the useful RPM domain. And anywhere else outside the optimal RPM domain, you will have huge consumption of fuel and huge losses. So in short, it looks more or less like a gas turbine in aviation. You get a very good optimal working RPM zone around maximal power, and the idling is just 80% of the maximal power, and while the airplane is taxiing on the ground before takeoff, it consumes a lot of fuel practically uselessly. And for a two-stroke engine, it's similar. So what you can have, either you get low power at the end, but you get a more or less acceptable efficiency in a wide RPM band, or you get huge peak power in a very narrow zone. Typical example of this was the 50cc Grand Prix racing motorbikes in the 60s and 70s. This time there were motorbike Grand Prix for 50cc mopeds. And you had 2 and 3 cylinder 50cc racing bikes. It's almost the size of the model engines, the small airplane model engines. You get? And the peak RPM was around 20,000. So noisy, like a bee. And they required 8 to 16 gears to operate. Literally 16 gears to operate, because the power band was so narrow. You get let's say around 20 horsepower out of 50cc without any electric control, just by flow mechanics. Note that the popular 125cc engines in Italy at the end of the 1990s, they had 20 to 30 horsepower out from one cylinder. And even these machines needed a gearbox of 6 speed. Okay, so you had a tiny engine and a large gearbox behind in the 50cc Grand Prix. And as the 50cc Grand Prix ended in the late 70s, you don't have so spectacularly peaky two-stroke engines these days. Actually, the 50cc GP was also ended because you had street legal machines that had 8 to 10 horsepower from 50cc, and the youngs were speeding at 100 km by hour with these machines without a normal driving license. So the development is a spectacular thing, but not always. Not always. Okay. Is it clear? Okay. Still, if you get any questions, you ask it on the chat window, or the present colleagues ask it in live. Actually, they don't have questions, so we go a bit further in this idea. So if we get an engine that goes upon the fluid mechanics, then let's try what we can do with the tools of the fluid mechanics. How we can improve the power by the tools and ideas that we usually use in fluid mechanics. Now, again, up. Further efficiency. No, I cannot write it. Efficiency increase. It can be based on fluid mechanics. The history says that the Germans in the Second World War were the first to develop rockets that can be used practically in the army. And for that, they used a large number of scientists at any level, from the simple computing guys to the theoretical background and to different professors in mathematics and fluid dynamics, or fluid dynamics. And after the Second World War, they were either captivated by the Russians and went to Siberia for further work, or they were captivated by the Americans and they went to the USA for further research work. And the smaller, simpler guys that were just computing guys or just test guys were partly left in Germany, either in West Germany or either in East Germany. And the life restarted, the civil life restarted after the war, and the motorsport also restarted after the war. What they had ruins, pencil or chalk, whiteboard or blackboard, and experience from the rockets. So the idea arrived around, let's say it's 1947, let's say. Then in a city of ruins, I don't know which German city was it that, but it was for sure in ruins, that in a cave, in a basement, some engineers designed the ZPH machine, which was a racing motorbike. And the name was, P was Petrushka. The Z was, I don't know which one, maybe something like Zollner. And the H was the third guy. And they all were related to the rocket industry during the war. And they had the following idea. You get still the piston. You get the cylinder with its ports, the transfer or scavenging port and the exhaust port. But the basic idea was the following. They knew from the rocket that if they use they play with cross sections and they make quite long diffuser cylindrical part and a shorter strong confuser plus an end pipe, they can play with the waves in the flow. How they can play with the waves? They can play with the time variation. You get this point, P, pressure at point P can change by the following way. You get the time, you get here the pressure in, let's say, bars, bar being roughly 1 atmosphere. T is the time in seconds, or not seconds, milliseconds. We are talking about short time here. And the pressure can be the following. You get here the atmospheric pressure P0, which is mostly 1. Well, let's say 0. No. P0, the atmospheric pressure. And how the pressure changes if you get this layout of exhaust system. At the start of the opening, there's a sudden decrease that helps the evacuation of the burned gases. And the evacuation of burned gases helps the enter of the gas from the crankcase chamber. And after a certain time, by the time the gas flow reaches the confuser, though the gas continues the going out, the pressure behaves strangely. There's a pressure wave that goes back in the opposite direction. So in this point, there will be a sudden pressure increase And a part of the fresh gases that went out in the exhaust goes just back in the cylinder. And if you can get the right RPM zone that allows the opening of the port for a given time interval, then you get a huge quantity of air mixture in the cylinder. So you get a considerable increase of your power. And this curve is guided by the following quantities. You get usually the mid-distance L1 of the diffuser. You get the mid-distance L2 of the confuser for closing. And also there is an angle, again an alpha 1 for the diffuser, and a larger alpha 2 for the confuser. These two angles and two distances describe this pressure variation. And again, you can have an ideal tuning of the system. You can choose your diffuser and confuser such a way that you get a considerably large power peak at given RPM domain. Okay? And nowadays, we are not using just one angle alpha 1 and one angle alpha 2. If you look at the scooters and the tuning exhaust of the scooters, you will see that the layout is such that you get a short starting, and then you get a continuously varying increase. So not just one angle, then some cylindrical middle part, and also a continuously varying closing cone and a narrow tailpipe in the system. So continuously varying angles. And here also continuously varying angles, continuously changing angle. This is what you see on the scooters. And the meaning of that is that if you get more than one angle in the diffuser and more than one angle in the confuser, then you get a larger power domain. Not a sharp peak, like in this case, but a larger, softer power domain. Okay? You can compute these things with any, even this one, with any flow dynamics software, finite element software. And it's not complicated at all. We get practices for that. Not for a complete system like that, obviously, but for a simple tube and simple pipe and to watching this wave variation, it's really easy to analyze.
So just to confirm, like this machine has like diffuser at the beginning and confuser at the end, right?
Yeah. A diffuser, circular or cylindrical mid part, and confuser. So every cylindrical part here, cylindrical part here, cylindrical part there, 3 cylindrical parts, and between them you get first a diffuser, then a confuser. And how the idea comes to these guys, to Soler and Petrushke, or Ziegler, started by Z. The idea was that they were using the same units in the rocket, but in the opposite order in a rocket. If you want to have a flow over the speed of sound, you get just the opposite order. Confuser to reach the speed of sound, a narrow gorge in the middle, and then a large diffuser for the flow over the speed of sound. Okay? It's just the opposite. If you see the different kinds of spaceships and the rocket motors of the spaceships, they get jets at the end like this. So it was just the reordering of the things. Okay? And this idea was so spectacular, but really so spectacular, that for 10 years, the East German motorbikes were the best of the world. For 10 years. Better than the West German motorbikes. Better than the Japanese motorbikes. And so one name is very important. The name to know was Walter Kaden. He was a German guy. He was responsible for the racing division of the East German motorbike factory that is actually known by MZ. It was IFA at the time, but it was MZ later on. And it was something like 1948. So he was seeing these guys racing on the streets in small local races, and recognized the idea and asked them to join the state-owned factory. As there was a socialist system, they had no choice to say no. So they entered to the state-owned motorbike factory. At this time, it was called IFA. What is the German name for that? Fahrzeugbau is the end. Industrialgeschäft, Fahrzeugbau, something like this. Industrial community of vehicle industry. It's roughly the translation in English. And from 98 till 1961, they were developing this idea, and by the mid-50s, they made the fastest motorbikes of the world in the Grand Prix races. And that's because the two-stroke engine has no valves, no camshafts, so it weighs less. And in motorbike racing, if your motorbike is lighter, then you get an advantage in the racetracks. The noise is not an issue. The consumption is not an issue in certain reasons, but still, you can consume a lot. And they was beating the West Germans, they was beating the Japanese, they was beating the Italians, everybody they was beating. And the technology and the computing algorithm were kept secret, state secret. And this was happening till 61, when one East German guy preferred not to exist in the socialist world, but maybe go to the capitalist world. And after a race, he was disappearing, and he was appearing half year later in Japan. Opa. He chose a different country and a different way of life. And he was not alone, but he took away with him his motorbike. And his second company after the NZ, it was the Suzuki company. And so MZ was around, it was the world champion. In the quarter liter or the eighth of liter, so 125 cc and 250 cc. But they still had problems with material quality and fiability. So the parts were broken, the parts were breaking, and so on sometimes. And miracle, by 1963, Suzuki was world champion. Okay, Suzuki. Suzuki was world champion with a surprisingly similar 125cc machine. So the idea was German, East German, but the material quality was Japanese. And manufacturing quality was also Japanese. And Suzuki's advantage lasts still these days. They are making really reliable, sound motorbikes. Not the fastest, not the most expensive, but really sound motorbikes. And cars also, still. But this thing gave them a big jump in the 60s, in the early 60s. Okay, it was a huge scandal, huge scandal. The Russian Secret Service, the German Secret Service, every Secret Service were chasing the pilot for a long time after. So it was a very important state secret, this idea. Okay. But there were also other kinds of flow control. So the Japanese were quite good, the Germans also were quite good. Flow control, port control. I'm just checking. Deflector on the piston, loop scavenging, yeah. We get, what was the name of that in English? Resonance tube, resonance pipe. Oh, this is something like this in English for this kind of exhaust. And also there are different flow control by valves. And it's a strange thing because we like the two-stroke for having no valves and simple structure, but if we want to have a larger power band and better efficiency, sometimes we use valves. What kind of valves do we use here? As we get a mixture of air and fuel, and the fuel contains for sure oil, we don't have problems with lubrication if we are using simple things. So it started quite early, around 1930s. Still, you get the company of DKW, the German motorbike company, that started to use admission membranes. So they just put an elastic metal sheet across the port, the admission port, and during admission, that elastic membrane could open and let the flow in. But when the flow wanted to go back, it was closed down by the pressure or a variation of the fluid. Admission, closing, admission, closing. It was a bending metallic sheet. It was perfectly working 100 years ago. The problem was the material fatigue. Even if it was made of the best quality spring steel, it could not last long. When I'm saying it does not last long, I'm talking about tens of hours, or maximum hundreds of hours. So on a test rig, it was proved that it's okay, but from a manufacturing point of view, it could not be manufactured cheaply. Though it was used in tractors, I will talk about, in slow rotating tractor engines where you don't have high RPM, but you need large cross sections to be opened and closed. But for small engines, it was not suitable. What was suitable was still the idea of Walter Kaden, still the Walter is there, 1950s, again MZ and Kaden, the same guy here. Kaden was a good engineer. He was not a scientist, he was an engineer, and he was good in manufacturing. And he had the idea of using rotating disc. For the inlet, And it's really easy. You get a tubular cross-section in the admission. This is the admission cross-section. And you get a rotating disc that goes through the admission canal. And you get omega rotating disc. And you get a window in this disc. If the disc rotates in synchron with the engine crankshaft, you can set this window such a way that it opens when there is admission. And after, the cross-section is closed. So what was the idea of Caden? It was not only using this resonance exhaust, but also to couple it with an admission control of rotating disc. You could use it with normal, let's say, spring steel. It was lubricated by your oil in the mixture. And you had a sharp and precise admission control. Again, it was a big invention in the 50s. If you know the car called Trabant, it's a two-stroke car of Eastern Germany, quite famous one. He had this kind of admission control. Okay? And again, this was on the Suzuki that won the World Championship by surprise. And the history says that even the parts were identical. So once the Eastern German guy had a problem with, I don't know, his crankshaft or piston, and Suzuki also was there in the 60s, a bit later on, the Suzuki guys gave them their part, and it was perfectly fitting. Sorry? Outside it was not the same, inside who knows. But the parts were more or less a bit similar, at least at the beginning. And one more thing, rotating this in admission, in the admission conduct. And one more thing that is important, that happened a bit, or that appeared a bit later on. Again, I've got to erase the board somehow. Now, one more thing for the control of gasoline engines. Around 1980s, we have the exhaust valve. And you can say, what? Exhaust valve in a two-stroke engine? In fact, yes. A bit different of what you see in a four-stroke, but still, there is, or there are. Actually, it's not used anymore. But you know, in the 1980s, there were a huge number of very powerful two-stroke engines. Motorbikes mostly, cars not so much. Motorbikes and also snowmobiles. In Canada, in the United States, on the north, snowmobiles are quite popular. And so they needed very strong, powerful two-stroke engines. So the Japanese have continued the work of Caden a bit, and as they had more time, more money, and better technology, they invented the exhaust valve that works by the following way, the two-stroke engine. You get the piston, as usual. You get an exhaust port in the cylinder that starts at a given height, and then you add something here. what you add something here is a vein, a closing vein that has got this shape. It's like a wedge. And it can be controlled either by springs, let's say it's controlled by spring, or other mechanisms, cables or electric motor. You get examples for all of these. And the idea is following. While the two-stroke engine is working at low RPMs, you don't need a so huge exhaust port because the burn gas goes out quickly, and also the gas coming from the transfer ports goes out quickly. So for low RPMs, you need a low exhaust opening cross-section. And with the increase of the RPM, you need higher and higher exhaust port. But you cannot do it directly. So if you make a constant low profile exhaust, you get good characteristics at low RPMs, but you cannot have high RPMs. Your engine is choked by this small cross-section. If you have a large cross-section, you can have a lot of power at high RPMs, but you get almost nothing as torque in middle and low RPMs, plus you get a huge amount of fuel that goes just through the exhaust. And for that, you use this vane. At low RPM, you can produce a small cross-section by closing vertically this port. And with the increase of the RPM, you pull this up till complete liberation of the cross-section. Okay, and if I'm not wrong, this was a system of Yamaha, Japanese manufacturer. At the first, they have a lot of commercial names. It was also used by Suzuki then, and maybe also by Honda for the 2cc engine, for the two-stroke engines. And it was a solution that was either used alone or together with the resonance exhaust. And this is the actual state of the art of two-stroke engines if you want to make a powerful one. So for snowmobiles, for chainsaws, for any kind of small engines, you may have inlet valves, you may have exhaust valves, you may have a resonance exhaust, and then you may have a relatively large power band, a huge, relatively big peak power, plus a relatively simple structure. But if you think about input vanes, inlet vanes, exhaust vanes, resonance exhaust, and you are more or less at the cost of a four-stroke engine. That's why you don't have two-stroke engines in big size anymore. The four-stroke engine above, let's say, of the size of 250 cc or even 125 cc is much more economic for the same amount of peak power. And also it's cheaper to manufacture. And these days with the emission control, emission standards, you just cannot put oil in the fuel and let it burn and going out the exhaust. Okay? So, you see, by the time we can make a very efficient and perfect and good two-stroke engine, it's useless, the market will not buy it for given reasons. But the story and the sparkling ideas are very interesting to see a bit. For any purposes when you get no emission standards, like snow bikes in the USA or motocross bikes, you get still two-stroke engines that remained. There are motocross engines with 700 cc, one cylinder. It's huge. You get large exhaust chambers that barely fit in on the motorbike. But still, they are important there. Okay, I think I will finish it for today. We have finished with the gasoline engines. And next week we continue with the diesel, two-stroke diesels, because they are interesting two-stroke diesel engines also, just for seeing how it happens. Note that in the large scale, diesel engines are still used in ships. Two-stroke engines in ships are very common, in large cargo ships, in container ships, and other ships of this kind. The four-stroke is also getting more and more popular, for example, in liquefied gas tank ships. But in the normal, cheap cargo ships, you get still the two-stroke engine. I will talk about it maybe next week, next lesson. So thank you for your attention. I hope that it was more or less interesting, and let's try to continue it next week. Note that we have a test in next week. I try to put it in Moodle so that your colleague online could also make this one. If you were just to, I would just give it to your paper, but I cannot. But you get internet access here, so you can make it just here in 10 minutes. 10 questions test with choice of answers. Okay?
Multiple choice answers.
Multiple choice answer. Okay, then thank you for coming, and this is the end of the lesson of today. Thank you.